doesn't matter. Okay. So, so how do we find this? Okay. So first of all, what do we know? We know very little, so it's difficult. So first of all, we should have an idea on, because see, it's very interesting that you can access this algebra directly without going through the root system and everything. First of all, let's make an important observation. Look at this. Actually, this is equal, right? Because it is either 0 or it coincides with that. Because this is dimension 1. So this is a vector space. This is either 0. So now, look at this bracket. So it tells me that if I have, suppose that I have the generators, well, first of all, I have to remind you what are the generators of a Lie algebra. Little note. This is a note, very general one. Do we know what the generators of a Lie algebra are? As you know, Stephen, the other students, they may not know. What do you expect it is generator of a Lie algebra? It's a very simple question.
Basis?
No. In fact, I was afraid of this answer. Certainly, a Lie algebra is a vector space. So one can choose a basis as vector space. This is fine. In fact, if you choose a basis for H, and then you take one element for non-zero for each root space, this will give you a basis as vector space of G. Now, I talk about a different thing. I talk about the generators of a Lie algebra, as Lie algebra. I don't know if you appreciate this difference. What do you expect it to be? Certainly there is also another structure on the Lie algebra.
A set of elements that generate the algebra
with a bracket, okay? Let's make a small example to appreciate the difference, which I must say that my friends in physics do not fully appreciate. No, which is true if you read the papers by physicists, they tend to confuse the two, and there is important difference. For example, let's look at SL3. If you look at SL3, take a basis for the diagonal, which are the Cartan, okay? Basis for the Cartan is H1 and H2, which is 1 minus 1, this is H1. And then you take plus 1 and minus 1 is H2. So H1 is 1 minus 1. H2 is 0, 1 minus 1. So you take a basis for the diagonal, okay? Fine. And then you can take, so there is the diagonal, this is the Cartan. So you have to take a basis of two elements, because I remind you that the trace is 0, so it's enough you give two elements. Then you have 3 elements here and 3 here. Okay? So the basis of SL2 is dimension 8. So dimension is 8, right? Because it's the 3 by 3 matrices with a trace condition. Now observe though that if you take, say you call this generator x12, x13, x21, if you take the bracket of x12, x21, what is the bracket of these two elements? Actually this is where we're saying obvious things. You didn't miss anything. So these are the elementary matrices, right? This is elementary matrix 1, 2. So this will give me, no, what am I doing? Sorry, this is 2, 3. I'm sorry, I'm just repeating. 2, 3. So this is E13, right? Is elementary matrix calculation. So you see that if you allow me to throw in the brackets, this element, you don't need to put it in, right? It's automatically inside as bracket of something. So the generators of this as a Lie algebra, so generators as Lie algebra are H1, H2, and then you have E12, E23, and then E21, E23. Because the same thing, this element you will get is the bracket of these ones. Now you may wonder, are there too many? These are not obtainable in other ways, but it doesn't matter. What I'm trying to say is that, see, you have 6 generators as Lie algebras. Instead, as vector space, you have 8. So, I mean, if you're allowed to take brackets of elements, you can reduce the number of generators. That's all. So be careful when you say generator, because it has 2 meanings. Perfectly legitimate, both of them. So, how do we find unique simple Lie algebra with that Cartan matrix? That is the question I wanted to face. So what you do is the following. Are we happy? Can I?
The cardinality of a generating set is the same for all generating sets. And for SL3, I will always find 6.
You can always add more generators, right?
No, yeah, but he's saying the minimal. So say, can you? I don't know the answer of this question. I know that there is a. I think no. Is it more? So the answer is inside the root systems. Why don't you ask me this question in 2 minutes so that you know what are these generators related? Because the point is, it's not that I'm just looking for generators as they are. I'm looking for a way of associating an algebra to a Cartan matrix. So these generators will be carefully chosen. It's not that. So it's not an abstract question. It's a very concrete. So, what you do is the following. So first of all, see, looking at this example is very fruitful. Because if you have a Cartan matrix, you know, so for example, what is the Cartan matrix of A2? We know the Cartan matrix of A2. Cartan matrix of A2. So I was very smart. I chose the polarization which is not the usual one. I hate myself when I do this. Let's choose a usual polarization that is in every book. It doesn't change anything, of course, because the base is the same. So let's call this alpha and this is beta. These are, choose this. So this is alpha plus beta minus beta minus alpha minus beta. So I choose this as the positive and this is the negative roots. What is the Cartan matrix? Okay, the Cartan matrix, see, has the same rank as the number of simple roots. Because Aij is parameterized by simple roots. The simple roots are the base elements. Then here, well, you have to compute it is -1. It's a small calculation because you have to compute this number. It's very silly, but I don't want to do it now. First of all, if you want to associate a Lie algebra to your Cartan matrix, you realize that it has to have a basis for the H, which is the same as the rank of the matrix. Because this will be a base for the vector space VR. This VR is not abstract, it's the H star, because this is where the roots live. It's a real form of it. So, what I'm saying is that if you have a Cartan matrix Aij, say I and J going from 1 to R, you know you're forced to have H1, HR. So these have to be bases for H. You don't know yet, okay? I'm just saying what we know, okay? This is a cheap thing, and you know the brackets of these elements. I don't know if you see what I'm trying to do. I'm saying, okay, suppose I have a Cartan matrix. What is the Lie algebra corresponding to it? Certainly must have the dimension of the Cartan must be the same as the rank of the matrix. And if I choose a basis, so you call H1, HR elements of H, which are a basis, the brackets must be 0 because Cartan is abelian. No, we're not happy. Then what I do is this, say, okay, remember that the base elements, alpha and beta, they correspond to root spaces, right? So for each alpha, sorry, so there must be some simple root, okay? If this is the rank, so I call simple root, and there will be minus corresponding to root spaces. So I call EI equals with the letter E. No, equals with no, it uses a convention that is his own. So I call E1 ER elements of G alpha 1. For the moment there are just, I'm saying what is the thing that I must expect? I must expect that there is a root space corresponding to simple root, right? This is what I expect. I don't know if, for the moment I have not done anything, okay? And then same thing, E minus 1, E minus R corresponding to G minus alpha 1, G minus alpha R. Okay, so these are root spaces, and we know that there is a pairing between this alpha 1 and minus alpha 1, which is the one I left here. Okay. And this, I can make a choice in such a way that EI, E minus I, is equal to HI. I can make this choice because I know that there will be an SL2 for each of them. So I impose this. So these are things I impose. I impose this. So I have these elements. Okay. So I've produced 3 R elements. our generators. Okay, these are called the Chevrolet generators. They will not be a basis. There will be not a basis because this example shows it already very clearly that they're not enough, right? Because the rank of SL3 is 2, and in fact we have 6 generators. 2 for the Cartan and then 2 and 2. Okay? So this will be now what is, so we have this, and then we have a condition. Of course we have to impose condition that HI, so when you do HI EI, this will be 2 times EI, right? Now it is a bit more general. You can show this is AIJ, your Cartan, EJ. So when you do the right, I like him because he totally writes something and doesn't say what the symbols are. And also if you take but I know luckily because so this will be, so if you put the minus, it will be the transpose, right? Hopefully.
So I'm sorry, at the moment you're working with an abstract Cartan matrix or one
No.
that's...
Yes, yeah, I'm taking a Cartan
And
matrix
constructing the simply algebra.
associated with it, okay? I'm saying, okay, let us, certainly I must have these elements sitting into it, this for sure. Maybe they are too little, but for sure I have these, okay? That is, now I should, to be really precise, I should introduce what is the free algebra generated by those elements.
Sure.
I didn't want to do it.
Right.
I'm just proceeding heuristically, right? Saying, okay, I have these elements, what are all the relations?
Right.
What is the free algebra? It's basically you take all the brackets of these elements and they will be infinite dimensional because the bracket of EIJ will be something that we call bracket EIJ, except that there will be these relations. That is all.
Because when you said you can show that HI bracket EJ is equal to that, I mean, that implies that...
No, you can
impose
show...
that.
No, because...
That, right?
No. You can show... Well, you impose it for abstract Cartan matrix, but if you're starting from a... Then you will have that. I'm saying if you have a simple algebra and you go through all the madness of producing Cartan matrix, HI you know what it is, EJ you know, because this is this thing, is this H alpha, right? And so the bracket HI, EJ, you know what it is, and look, it's really that, this HII. Well, it has to be shown though, it's not obvious, because we know that HI, EI is 2 times. We know this when I is equal to j. We don't know when I is different from j. It's not hard to show, but it requires some analysis of the root system. So these are the, and then you have EI, EJ, which is 0, right? No, it's not 0. What am I saying? You have that, yeah, this here. Okay, now these relations, if you have the free algebra, are not enough to define.
Who is H? The vector space?
H will be our Cartan, which I don't know what it is. So it's what Stephen was telling me. It's like what you have. This is the thing is that if I already have a Lie algebra, I associate a Cartan matrix and notice all of these facts. If I have a Cartan matrix, I say, okay, let's take H1, HR. I don't know what they are. Let's take this E like this and build the most general Lie algebra satisfying all of this. Then I claim this is a simple Lie algebra which datas Cartan matrix. You see my point. Now, This is a problem that people asked, Chevalier asked himself, and they thought that this would be enough. But this is not enough. There is more. So if you try to impose these conditions, you will get infinite dimensional algebra. What I'm saying is that the most general, and it's called free, Lie algebra satisfying these relations is infinite dimensional. In order to obtain a finite dimensional algebra, you need an extra condition on these generators. It's like if you have some algebra and you quotient by something, you go down with dimensions. At some point, you get to a finite dimensional vector space, maybe. And this is the same thing here. You quotient by a Lie ideal. By an ideal generated by this relation is a Lie ideal. So this was another course after the one I gave to you. I make another course which is this. But so the extra relation that you have to add are called the Serre relations, because Serre was the one realizing first that these were missing, and these are the following. He writes like this, okay? I'm writing what he writes, but I explain. Adjoint of E plus or minus I, 1 minus Aij, E plus or minus J. So these are called the Serre relations. What does this mean? Because written like this is not very clear. It means that you are taking so you're taking the bracket of things. Boy, what are you taking? So you're taking I'm sorry, I forget what they are. So you're taking like brackets of element like this. So you're taking brackets that do not stop after 2. You're taking 3-4 times brackets. Now, I'm sorry, I don't remember what you put, plus or minus. He writes like this, I write in a different way. I can check the book by Varadarajan and come up with the right ones, I forget. Okay, so what is the time? I don't want to, because this is the
12:30.
30. Maybe I speak 2 minutes and then we stop, because I feel guilty that the organizers are all not here. 2, because there's, you know that they had the 2 different accidents. Marta Morigi and Fabrizio Caselli. One had a bike accident and is in bed for a month. The other one has a domestic accident and is for a week she's and then now Nicoletta Cantani said, I'll be slightly late and she's not showing up. Now I'm worried because this seminar seems definitely to be worrisome. Okay. I'm not sure how much we will use this going back, but it's very important, although there is a way to go directly back. So you start from Cartan matrix, and there is handed you freely this thing, is directly, immediately. The proof is not immediate at all.
So with the Serre relations, we are sure that it's finite dimension.
Yes, that's a surprising thing. It will go down, not only is finite dimension, it's isomorphic to the one that has that, as is Cartan matrix. It's like a very peculiar fact, and it's not trivial to prove. You need a lot of representation theory to do this. It's not trivial.
So to speak to Lorenzo's point, these are all the relations you need, right, to get finite dimensional one.
Right.
No more. Yes.
Yes, but his question was different. Say, okay.
Right. Minimal generators.
Yeah, he says, okay, let's take other generators.
Right.
Maybe we can find another set which is different from this, and I don't know. It's not coming from this recipe. Okay. Now, I want to say something that will come very important to us, and precisely the group. Okay, what do I want to say? No. Yes, the group counterpart of this thing. So there is an SL2 which is embedded into our G for each root. But even if they're not feeling well, they know that I will question them and test them when they're back. Fabrizio called over the phone and said, "Don't worry, you will be tested when you're back to see if you studied." Okay, so say for each alpha in our root system, we know there is SL2 embedded into G, and what is it? He writes explicitly, okay, he says, great, you have the 1 minus 1 is going to what I call H alpha, which he calls, no, he makes a special choice. So for each, so this we have for each circle, but he now wants to consider alpha simple, okay? He wants to take just the simple ones, and this for simple he calls, so you know that, so you have alpha 1, alpha r, simple, and for each of these ones he writes an embedding which he calls, rho I. Oh God, they don't know what's the same for the group. So there is rho I going from, so the Cartan element in SL2 there is just one Cartan, goes to this, which he calls, he defines HI. It is common to define H alpha I with HI. Then embedding of 0, 1, 0, 0 goes to this X alpha I, which he calls EI, as we did for that. And 0, 0, 1, 0, the X minus alpha I, he calls E to the minus I, EE minus I. Okay, great. Now, we should know, but we don't, because we have not taken any decent course on Lie groups. Do we know that there is a, how much do you know about Lie groups? Where did you learn it?
The group theory from physics.
Ah no, then you know. Then you know. Okay, so it's, there is exponential morphism going from SL2 here. We're over the complex, everything over the complex. Exponential morphism going to this, the group. Now, it would be nice to have this, do we know a result saying it or we don't know? We don't know. I tell you, there is this closing which he very casually defines it in the same way, but it's very, what can I say, it's very dangerous to denote it in the same way. Let's call it with some tilde, something to, because it's not really the same. He uses the same letter, but no. Let me just say something, okay? There are two issues here. First of all, if you start with a morphism of groups, you take its differential, you obtain a morphism, H is not the Cartan, say let's say something different, sorry, say G prime. So this will give you, so if you take a morphism of Lie groups, which is a differential map, which is also a group homomorphism, if you take its differential and the identity, this differential will give you a map between the tangent spaces. That's fine. One can show that this diagram is commutative with the exponential. Okay? This is already something which is remarkable, that the exponential will go where it should go. Not harder to show, but there is some, you need some argument, right? Because it's not obvious that, I mean, if you have a map here, why should you go to the map here? There is no need, okay? But we started from a map from the groups, and then we differentiate. Here we're doing something which is the opposite. We're starting from a map of the Lie algebras, and we integrate the map instead of differentiating it. So there is, so this is one, so this is one theorem, theorem 1 for the theory, that we will do in the course of Lie groups. Now there is theorem 2. When can you integrate? So when you have G prime, when can you do this map, right? Once you have this, the exponential will commute. But how can, it's not that you can always integrate. It turns out that if you have a simply connected groups, you can integrate. And the reason is because you will build, see, because let me tell you the intuitive proof of this theorem. So here you have the map on the tangent space, okay? What do you have to do? Well, this map will provide a neighborhood, so to speak, of isomorphism. And then you have to, this has to become global, okay? How do you make it global? You remember in my class in topology that I had you prove that every connected group is generated by any neighborhood of the identity, right? So you use the element of the neighborhood of the identity or produce the whole group. So any group element can be reached by multiplying this. Except that you can reach here by multiplying like this or multiplying like this. You could reach two different paths. So you will make sure it's simply connected so that the different paths will, this is not a proof, okay? This is just an idea on how the proof is built. But this is to justify. Of course, in this very, what can I say, in this very optimistic book that assumes to the reader to have the knowledge I have and maybe more, which I don't say I know very much. I know something about this theory. It doesn't mention any of these theorems. So it sort of integrates freely and happily.
It is obviously unique.
Yes. No, it's... if it is connected and simply connected, the map is unique. No, but the theorem is not like a trivial theorem. You have to prove things in this theorem. But come to my course on the groups. We do everything. We will do everything. They convinced me. I wanted to do algebraic groups. They convinced me to do Lie groups. So what I wanted to say, I want to finish early, but no, okay, just say one thing, is that what is the exponential of these things? So exponential, so say h, no, what is it called? Oh boy, whatever. So this will be t minus 1, where this is e to the h, e to the minus h. Then the exponential of this one is 1, 1, and u. So if you put something here, right. So if you say t, and the same for the other. So you have an embedding of these three elements, the Cartan and the other, into this, and this. These are very important, but I think I will stop here. I will continue this thing next time because there are more things to say. Because now we want to transfer the knowledge of the Lie algebra to the group through this exponential. That's what we do. What's the time, Stephen? I wanted to finish early, but I'm sorry.
It's 12:40.
12:40. I think it's fair because 3 organizers are missing and it's not right. I hope you won't mind if we finish a bit early. Now I call Nicoletta.